Nowadays, it is critical to lead effective performance of your work through all the phases of your project, and technology is available to achieve it. This is where BIM became essential. Building information modeling is perceived just as a 3D modeling, but is more than that. It needs to be a smart 3D. The workflow allows to exchange a lot of data, using this information to design, visualize, and simulate projects that will help to manage building faster, reducing costs and environmental impact, and mainly to satisfy your customers and stakeholders. This leads to a point where it's need to model in a more accurate way, with a more integrated teamwork to execute projects more efficiently and successfully. As shown in this image, BIM information modeling helps to create advantages in all the segments of the project lifecycle, and where implemented a fluent workflow of data is essential. In this video, we are going to show the workflow between Advanced Design, Revit, and Advanced Deal. In particular, we are going to create a model in Advanced Design and then export it to Revit, where we are going to check and make some changes, and then coming back to Advanced Design and synchronize the model, updating all the information. Once we have done this, we will run again the model in Advanced Design, and we will export all the information to Advanced Deal, where we are going to design some of the connection. Done this, we want to update our model in Revit, as it is our lead software, to then create the final drawings. To build our model in Advanced Design, the first step is to set subsystems, columns and beams in this case, as it is a frame structure. We then enable a level of 3 meters for our column, and we draw our element, which characteristic can be found on the Properties menu. We copy it 5 times at a space of 4 meters. To copy, we can also hold the Ctrl button, and this will allow us to copy our element by dragging it. Once we have drawn our column, we are going to create the beams. As we have 2 directions, we set the 2 subsystems, one for X and one for Y direction. We draw our linear element, and then we change the section to be a UB1. To copy them, we select the vector and the number of times we want to repeat the command. The preview always helps us to create a copy or to move an element without mistakes. Another way to copy is selecting the whole length and then subdividing it by the number of times we want. Another tool is copy by rotation, in which we define the origin and the axis. The preview helps us to understand which direction will be the right one. To help us to draw our structure, we can also use non-structural elements, such points, line, grids, etc., that will help us to draw and create our structure in a better way. We use the line to guide us to calculate the distances between the elements and to copy them in a quicker way. By default, the main axes of all columns are looking towards the X direction. We want to change instead their direction looking at the Y axis. To do that, we are going to place non-structural points that will help us to give the wishes direction to all our pillars. First of all, we are going to change the angle of 90 degrees to all our column. And then, thanks to the point we have inserted, we can give the direction wanted to all our column that will be looking at the point placed. Finally, we set the direction of these 3 columns towards the point number 1. We are going to draw now the bracing. We create the subsystem, we modify the section of the linear elements, and then we can insert them. Bracings can be set also as a tie or strut, working in tension or compression only. With this kind of element, it is required to create a nonlinear static analysis case. We are going to draw also some plate elements for the lift. We set a subsystem for the wall with a level enabled, and then using the snap of the linear elements, we are going to place them. We can deselect an element of our subsystem, just double-clicking them. This will help us to create different views and to select and amend the elements we want. We can also define openings of any shapes, drawing, for example, a closed line, and then using the Create Openings tool. In this case, we are going to create the openings for the door of the lift. Another way to outline openings is drawing non-structural lines and use the Subdivide tool to shape the opening. We place now the supports of our structure. We select our columns and then, right-clicking, we can have access to the quick menu that allows us to insert the supports for the selected elements. We set the subsystem and then we select all the supports using the Select by Criteria feature, and we change the subsystem group. Supports can be rigid, elastic, or working in tension or compression only. Another important feature is the footing dimension that will allow you to give the support the section desired, for example, when you export the model to Revit. It is also useful when it is required to calculate the elastic support, as we can give the soil condition of our structure, and it will calculate automatically the stiffness to give to our support. In the same way, we are going to create the support for our lift. Advanced Design will set up automatically that you need a linear rigid support, and then we will use the Select by Criteria to drag into the right subsystem. Advanced Design gives you also the chance to set for each element eccentricities. This will be of great help to project your structure, considering all the eccentricity that there will be during the construction phase as well. This will be helpful also for the workflow, for example, between Advanced Design and Advanced Steel, in which you will set your eccentricities and also levels. If you want, you can consider them or not in the calculation of your model. We are going to isolate now our beams in order to place load areas. Load areas are non-structural entities that spread the loads between the elements which define them. These entities won't be meshed during the calculation. The main features are that you can choose the span direction, we can create rigid diaphragm, and we can give the self-weight of the slab. We can create our raw materials and then set the density and thickness. If you want to mesh the slab with the structure, we can as well create plate elements that will be meshed within the structure and will give the stiffness required. Next step is to set the height of the column. In this case, we are going to create, for example, two different levels of columns, placing them in different subsystems. The one, external, let's say, will be 12 meters high, while the internal will be 15 meters. In a workflow perspective, we are going to make some splits of our columns. This will allow us, when we will export our model to Advanced Steel, to export the forces when we create the splice connections. We select then the elements we want to copy in the different levels. To do that, we can use the Copy tool or hold the Ctrl and drag the elements. We are doing the same for the walls. copy the element, we'll keep the opening as we wish. We are creating then the roof of the lift. We can create a plate element, or if we have a specific shape, we can also draw any closed shape and then convert the line to a plate element. We can also convert them to linear elements, so it is possible to draw lines and then convert all of them in beams or columns. We can also make change of the height of only some of the element without the need to create any other level. Once we have built our structure, we are going to place the loads. To do that, we just select our load areas, and with the right click, we can have access to the quick menu that allows us to insert loads on the elements selected. We create, in this case, dead loads, live loads, and wind loads. Loads are as well entities. To copy them, we can also hold Ctrl and drag them. To make changes is quite easy. We select the load and make the amendment required. On the top of the building, we are going to put a different kind of load. Wind loads can be automatically generated. In this case, as it is only a sample, we are going to place some point loads, just to show different combinations. You can set as many combinations as you want, and divided them for the different verification for steel, timber, and concrete. You can also use the simplified combination that will generate automatically combination for the code chosen. Now our structure is complete. We verify that everything is fine, and then we can run the model. Once the model is analyzed, we have a look to the forces and moments in the structure to compare the result of advanced design with the ones of the other software, checking that the workflow of information is correct. We can save views of the results. This will be updated if we make any change in the structure. Then we export the model to Revit. Once imported, we can see that section, orientation, and eccentricities of the elements and the loads match the one drawn. We open the analytical model and we check that the analysis imported gives us the same results of advanced design. We choose the moments and we select the right combination. We make some changes then to our structure. We make some change in the front columns, which section will be increased, while the section of the roof beam will be smaller. We then export the model with the changes, and we are going to synchronize the model in advanced design. The changes of the section are shown in blue. First, we are going to synchronize the beams of the roof and then the columns. We accept the changes made and then we apply them to the structure. Now our model is updated and we can run the analysis again. We have a quick look that our results have been updated, and then we export the model again. We export in SMLX file for advanced steel and in GTCX file for Revit, where we will update the result of the analysis. This result can be then used in Revit, for example, to insert rebars, etc. The model now is fully built and synchronized between the calculation software and the architectural one. So we can go to Advanced Steel to create our connection. We import the model, and as you can see, the forces have been imported in the nodes and splits as well. We create initially our splice plates. We assess the connection volt and we choose the connection we want to insert. To check the connection, we can select to use the forces brought from Advanced Design. We have a look to the report, where we can see that the forces has been correctly imported. To check the forces in Advanced Design, we select our member and open the detailed diagram, where we look at the forces in the node in which we have set the connection. We create as well a column bin connection. Advanced Steel Connection Volt create automatically the connection with the parameters indicated in the green book. Finally, we create the base plates and we copy them in all the column. Now our model has also the connection inserted. To export them, we first need to number them. Then we can export them to Revit, where we will have the model complete. In Revit, we go to the Advanced Steel Extension tool, where we synchronize the model. We filter the connection and we apply the changes. We can see that the connection in Revit have full intelligence and can be amended and modified as we wish. Now the workflow is complete. We have the full data shared between the software and we can create reports and drawing.